Hello, my name is Frederik Wulle and I would like to welcome you to my talk about our research in time-optimal path planning of multi-axis CNC processes with a focus on orientation tolerances. To explain what is this topic about and for which technology you can use it, I give a little example. This example consists of a 3-axis kinematics with 2 translational axes and 1 rotational axis. The tool center point is marked by a red circle and the paths by a red line. Now the kinematics should move around a workpiece with an edge. Most commonly path planning approaches orient the TCP orthogonally. Here the kinematics has to reorient in the corner and the path velocity is 0 for a moment because of dynamic constraints. Obviously, this movement is not optimal, neither in time nor in processing. A well-known approach in CNC applications to improve the motion in the corner is to round the path, as you can see here. This movement stays not exactly in the trajectory which was defined before, but the TCP velocity stays high and the dynamics, so the jerks and all the kinematic variables are not so high to damage the kinematics. In our paper, a method for path planning is described that uses tolerances in orientations in multi-axis applications to increase the TCP's velocity. Possible applications are welding, 3D printing, etc. that have process-dependent orientation tolerances. Therefore, I describe first orientation tolerances, and then there is a formulation of the optimization algorithm, and with 2 examples I will show you the results. On this slide you can see the most important variables as they are the tool pose, the axis positions, the path coordinate and the time, and their relations to each other. The orientation tolerances are normally described by angles relatively to the workpiece surface. On the right side you can see delta. The delta is the difference in orientation between the tool orientation and the workpiece surface. This is our major orientation tolerances variable. The range of delta, so to say, the tolerances in orientation can be described as a cone based on the TCP and the surface with constraints that are technologically dependent. Here, the orientation of the tool can rotate around the Y and the W axis, whereas the rotation about the U axis is not concerned here. Now the question is, how can we describe the problem in a proper way? And we see the problem of tool orientation in path planning is based on two major questions that are coupled. One question is how to choose S of t, so the path, when Q of S, so the pose, is given to achieve minimal processing time. So we see we have a given Q and we want to have S of t. On the other side, we have the question how to choose Q of S, so the pose of the kinematics, when S of t, so the path, is given to achieve minimal processing time. For the question of the usage of tool orientation, we have a coupled situation here, and the optimization problem has to deal with both of it. One solution for the second question was delivered by Verl, and now here for our problem adapted by the orientation tolerances that are included by delta. You can see the optimization formulation and the formulation of the orientation tolerances included in the second line in the dynamic equation. I do not go into detail about all these equations, but in the last lines you can see the constraints of the orientation tolerances and also its velocity. This formulation was implemented in MATLAB by using Casadi and the IPOP solver. Now I would like to show you some results of this research. For the aforementioned problem, a tolerance in orientation about 30 degrees was defined, and now the corner motion is much faster. But yet it still stops in the corner due to the orientation constraints, but not as long as the initial solution, as you can see obviously. The validation was also done on an industrial CNC 7-axis kinematics that you can see here. This has a twin-cut CNC control system that reads the G-code, executed this in real time, and the task here, a representative task here, was to move along the green line that you can see on the table and have here a synodalious orientation that you can see in the translucent purple surface. This is marked by the dash path. The tool center point is marked with the green spot. Three different tolerance angles were set for this validation. In the first video, we set a tolerance angle to 1 degree, so it's more or less exactly the same charge-set trajectory that we set right before. For this, you can see the motion needs about 3.8 seconds. "15 degrees" in Orientation tolerances give more freedom in the orientation, obviously, and now the motion takes just 3.5 seconds. Orientation tolerances about 46 degrees can totally smooth the trajectory. You can see how fast the kinematics can move this trajectory along. To sum it up, you can see which progress in time we could achieve by the use of orientation tolerances in path planning by this example, but this approach can also be applied in different processes and applications to decrease the processing time. Some relative research topics can be seen in collision avoidance and real-time implementation of this optimization in the CNC tasks. Thank you very much for your attention, and I'm open for questions.